I am very grateful for the warmest invitation of Yaroslav to participate in this conference. This is a great honor for me. I'm representing Paton Electric Welding Institute. This is a quite big institute in Ukraine, and it counts up to 1,000 employees. Half of them is scientific researchers. And I can state that Paton Electric Welding Institute is a flagman of Ukraine and actually Eastern Europe concerning welding. And this is a great honor for me to present my institute. And today I will speak about high hardness, high entropy alloys obtained via arc additive manufacturing. Actually, what does it mean, high entropy alloys? High entropy alloys is in difference from conventional alloys. They contain from at least 5 elements, and there are no main element in this composition. Each element presents in relatively equal proportion, and in this case you have oversaturated solid solution. You can see, just a second, you can see, and in this case you have changed phenomenon, physical laws such dislocation, movement, diffusion, etc., because you have another crystal type of crystal lattice. Actually, you have the same crystal lattice, but at the nodes you have different types of elements. And this new type of materials opens way to create something new in very important branches such as cosmic, nitrogen, energetic, chemistry, because these materials possess high cryogenic characteristics and high corrosion resistance, etc., etc. And particular in my presentation, I will speak about high hardness, high entropy alloys. Let's start from the beginning. Why arc additive manufacturing? To perform wire arc additive manufacturing, firstly you should have wire. And in our work, we suggest and invent metal powder cord wire. What does it mean? We have a metallic shield, and inside this tube we have a mixture of pure metals powders. For example, for classical composition, counterclassical composition, it's nickel, cobalt, chrome, and manganese mixture inside tube. This is unique approach. Why? Because if you want to create some hard material with solid wire, you should perform drawing. However, if you have very hard material, it is impossible to draw it to small diameters such like 2.4 millimeters. Because strain hardening and cracks, or even if you not have cracks, you should perform intermediate softening annealing. So the price of such material will be costly. In our case, we create metal powder cord wire. We can govern the composition inside the wire, actually chemical composition of final products. And we needn't intermediate softening annealing, we needn't vacuum or argon atmosphere. So this is our benefit. And further, we use this filament as filament in direct energy deposition system. We can use MIG and MAG welding or TIG welding, or another one application we can use atomization. It means that from this metal powder cord wire we can directly obtain spherical particles of high entropy alloy composition. Next step, we perform via arc additive manufacturing, and we have created the sample of the wall with high entropy alloy composition. Here it is presented the welding mode. for manufacturing. In our case, as we have wire with 2.4 millimeters in diameter, welding current is approximately 300 amperes. It's quite big, and we obtain a bulk sample of high entropy alloy. And here we have a number of advantages. For example, to produce such dimension of high entropy alloy with conventional metallurgy, we should have a furnace with atmospheric shield, vacuum or argon to prevent oxidation, and be time consuming and energy consuming. And several hours it is need to melt such volume of metals, and in our case we spend at least 15 minutes to produce this sample, bulk sample. The first step of the characterization, in our case obviously it was scanning electron microscopy with characterization of chemical composition. In our case we find out that we have obtained high entropy alloy composition with uniform distribution of each chemical element, and obviously this is micrographs. In secondary electrons, it reflects the grain boundaries, peculiarities inside grain boundaries, and Bayesian mode at backscattered electron. They show phase composition. We see that we have different type of grains, and in a backscattered electron, we have no contrast. It means that this is a uniform one phase. But yes, this is not clear evidence that we have one phase composite. Also, it was performed calculations using thermocalc with this chemical composition, and it shows us that we have single phase FCC with temperature of liquidus 1400 and solidus 1390 degrees of Celsius. Also, few words back side, we have made X-ray diffraction, and there was clearly peaks for FCC phase. So it's really FCC phase. X-ray maps with scanning electron microscopy shows the uniformity of distribution of elements, and from bottom, middle, and top part of the billet. So through whole volume, we have uniform distribution of chemical elements. Next step, also for characterization, we have made electron backscattering diffraction. And from also strategies from bottom to top. We have observed dependencies that at the bottom part of the billet, the grains are more fine than at the middle and at the top. This is connected with the heat flow, because first layers of the deposition have much higher cooling temperature on a cold substrate, and after several multi-layers deposition, the cooling conditions becomes different, and cooling speed becomes more or less, and we have obtained more and more big grains from bottom to top. And if we consider the middle part of the billet, we have steady state mode and relatively uniform distribution of grains. So if you want to print bulk billet, you should cut first 3 layers of deposition and last 3 layers, and another one billet will be solid and uniform with uniform mechanical properties. Next one, also next level of microscopy is transmission electron microscopy, where we also saw the distribution of dislocations, bottom, middle, and top part, and the same dependency. At the bottom part, there are almost no dislocations, low dislocation density, and moving topward, we have observed increasing of dislocation density. It is also connected with solidification process. Also, we have observed artificial elements, let's say. This is complex titanium, manganese, chrome, aluminum inclusions with spherical shape. This is connected with purity of the powders and solidification process. Mechanical properties. Mechanical properties were analyzed from bottom to top and also with cross-section. We clearly seen that we have more or less uniform distribution of mechanical properties. As I told you before, at the bottom part we have more high hardness and mechanical properties. This is connected firstly with grain size, and second one, it is a small mixture of deposited metal with substrate. So this could be called the buffer layer, which we eliminate from consideration. Another type of chemical composition, as I told you at the point of creation of metal powder cord wire, we can govern the chemical composition. In this case, we exchange manganese with copper. And as you know, if you have a high amount of copper, it is really very hard or impossible to obtain a sample without hot cracks. In this case, yes, we have obtained hot cracks enriched with copper because solidification temperature of copper is relatively low. However, when we use tungsten ion gas welding, we eliminate hot crackings. The benefits of using copper in such complex system is that it could be applied in atomic energetic. And the next one is high hardness, high entropy alloy. In this case, we introduce in alloy system aluminum and little bit of refractory elements, tantalum. And as printed material, we obtain biggest hardness of 450 HV. It's really high values comparable with armor steels. And it was surprisingly that after printing, actually multi-layer welding, there wasn't any hot cracks and cold cracks. However, the plasticity of such composition after printing was extremely low. It will near 2 or 3%. It's absent of plasticity. We perform heat treatment of this material with 1000 degrees of temperature, 1 hour, and after that quenching in water. We obtain dissolution of excessive phase, actually composition of tantalum with another element. And we obtain significantly increase in plasticity with conserving of high level of strength. In this case, we have printed volume sample of high entropy alloy with yield stress up to 1300 MPa and elongation to failure up to 15%. It's really good results. Another application of using such filament is atomization. Atomization and obtaining of spherical particles with uniform high entropy alloy composition. And this is a way to use this material in selective laser melting or electron beam melting process for 3D printing actually. Another one application, we have collaboration with Split University, with Professor Misha Chetipovich, and we have made the following routine. We have printed bulk sample. After that, we perform hot rolling and obtain flat plate cut from that target for sputtering in magnetron diffraction. And also we have made some experiments and research with hot rolled material. We perform study of different values of temperature and different times of heat treatment. And we have solved dependency that at 600 degrees we have very stable properties. Next step, at 800 degrees we have decreasing in mechanical properties, actually hardness is decreased. And after that in 1000 degrees we have again increasing in hardness. And what we have seen in microscopy investigation, that at 1000 degrees of temperature and 1 hour, we have fully recrystallized grains and very grain fine microstructure, with in accordance to Hall-Plage law, leads to such increasing in mechanical properties. And the next one application is from that target, sputtering target, using magnetron diffraction. We have made high entropy alloy coatings on such cylindric samples. And it is very interesting that the height of this coating up to 2 microns and very fine microstructure with nanometric sizes with crystallines like pyramids. And these results is ongoing experiments and research. So, as a conclusion, I will not read this. I can say that application of metal powder cord wire opens way to print a broad chemical composition of different high entropy alloys in a time-consuming way and economically beneficial with energy resources. And we have a lot of possibility to create very hard materials, which is impossible to use when we use conventional solid wires, solid welding wires. And I am very grateful to all my friends and co-authors in collaborations. Thank you very much, and looking forward for your interesting questions.